Okay, everyone, we're on section 12.4 now, which is the cross product, and this is another way that we can combine our vectors together, not necessarily with multiplication, but kind of with the same sort of properties, and it's kind of a continuation of a different way to do it other than the dot product. So it will be useful in the future to have vectors that are not zero, that are orthogonal to two other vectors. And we'll use this idea when we get into the next section in 12.5 when we talk about lines and planes. And so this idea is called the cross product. And the cross product, as opposed to the dot product, actually produces a vector. The dot product gives you a scalar, just a number, but the cross product will give you an actual vector. And so there are different ways to do the cross product. I'm going to do the Cal 3 very mathematical way to do it. And if you do linear algebra, you'll probably see this way. Usually physics or engineering will do it a slightly different way. So if you know how to do the cross product in a different class a different way, that is perfectly okay. But the definition is that if you have two vectors, A and B in this case, then the cross product is a formula. It's A2 times B3 minus A3 times B2, and then A3 times B1 minus A1 times B3, and then A1 times B2 minus A2 times B1, which almost no one ever remembers. So we do it in terms of matrices and determinants. So the cross product is the determinant of a matrix, and we usually write it like this way right here. And we find the determinant of that matrix. Now, if you do that, you get A times the lower part. So just these two columns are these two here. That's what gets multiplied by A. And then you have the J gets the first one and the last one. So that's this column here. Notice also with J, there is a minus sign in front of the J. So right here, oh, sorry. I don't know if you all saw that, but my entire screen just went white and then turned back around to all the words. Anyway, so there's a minus sign right there. And then the J part, or the K part does the first two columns. And the vector A cross B is a vector that is orthogonal to A, and it is orthogonal to B. So you get a vector that's orthogonal to both vectors. One such set of vectors would be something like your I, J, and your K. I is a vector, is orthogonal to J, and K as well. So just kind of, that's just an easy, simple one. So this says find the cross product between A and B and verify that it is orthogonal to both A and B, which is not terribly hard to do. So my cross product, if I do A crossed with B, I do it, like I said, the very mathematical way. I put an I, a J, and a K, and then I'll have my vectors 2, 3, 0, and 1, 0, 5. And you might wonder, well, what if you did them backwards and put the B on top of the A? Are they the same thing? And it's no, not necessarily. They're not. So this would be the lower part, the determinant of the 3, 0, 0, 5 times the vector I, minus J does the 2, the 5, the 1. Oh, sorry, not the 5. The 5 on the second row, isn't it? Sorry. The 2, the 0, the 1, the 5 with the J, and notice the minus sign in front. And then the K does the lower left, the 2, the 3, the 1, the 0. And it takes a 3 by 3 matrix and turns it into 3 2 by 2 matrices. And so those matrices, you just multiply your diagonals in each one. And so this would be 15 minus 0 on the I, this would be 10 minus 0 on the j, and this would be 0 minus 3 on the k. So it's always top left to bottom right minus bottom left to top right. So that's the direction we're going in here. And so if we simplify this, this is 15i, negative 10j, and minus 3k. Or you could write it in the same notation we started the vectors in as 15, negative 10, negative 3. And so that would be my cross product. That is this vector here. This is a vector orthogonal to both of the a and the b. And I can verify that for you. I'll do that on this one. So if you did the vector 2, 3, 0, that's your a, and you dotted it with the 15, negative 10, negative 3, if they are orthogonal, the dot product is 0. That's what we just looked at in the last section. So we'd have 2 times 15 plus 3 times negative 10 plus 0 times negative 3. That's 30 minus 30 plus 0, which is 0. Or if you do the other one, the 1, 0, 5, dotted with that same 15, negative 10, negative 3, I would have 1 times 15, 0 times negative 10, and 5 times negative 3. That's 15 plus 0 minus 15, which is 0. So since they both come out to be 0, that means that they are orthogonal to that vector. And since both of them came out to be 0, then they're both orthogonal to the cross product. Let's do another one. This one has functions in it instead of numbers. I think that's probably okay. Let's do one with functions. You'll notice that we'll do more and more functions as we go along the way as well. So if I do A cross B, well then I would do, just like I did in the last one, I'd have an I, a J, and a K. And then my first vector is T cosine T, sine T. And then I have 1 in front of the I have a negative sign, and I have a cosine. So I get the lower right, I get the cosine, the sine, the negative sign, and the cosine on the I, minus, for J, I'd have the T and the 1, and the sine T and the cosine T on the J. And that cosine doesn't look very pretty, does it? Try that again. And the cosine T. And then for the K, I'd have the lower left, the T, the 1, the cosine T, and the negative sine T on the K. And so I would do the diagonals again. Cosine times cosine, which would be cosine squared. And then minus the other direction, sine times negative sine is negative sine T. Squared. Oh, well, yeah. That would be multiplied by I. Then I have a minus. I would do T times cosine, which is just literally T times cosine T, minus 1 times sine, which would be sine T. Going the other direction. And then going the last direction, over here, I would have t times negative sine, which would be negative t sine t, minus cosine t times k. So this first one, well, I kind of wrote that kind of bad, I think. It's not technically negative sine squared. Oops, it's really, let me write it better than that. It's not really negative sine squared. It's really negative sine times sine. So the two negatives cancel to give you a positive sign. So we'll end up with cosine squared plus sine squared minus t cosine t minus sine t on the j. And then if you want to factor the negative off, you can. You could make it a minus, or you leave the minus in there. It doesn't really matter. Negative sine t minus cosine t. But the important one is the first one, cosine squared plus sine squared is just 1. So this part will just be I minus t cosine t minus sine t times j plus a negative t sine t minus cosine t times k. So that doesn't come out nearly as good as, like, for instance, the other one we looked at just a while ago. And that's okay. But this is your cross product. And I won't verify both of them, but I'll verify one of them. If I do the first one, A, if I do the ti plus cosine tj plus sine tk dotted with the one that I just came up with the I minus, actually, let's put the negative through here so we can make it all positives. I'll end up with a minus, let's put the sine t part first, do minus t cosine t j, and then plus negative t sine t minus cosine t k. So if I dotted those together, I'd multiply the first ones together, which would be a t times a 1. Then I would do the ones in front of the j, which would be a cosine t times a sine t minus t cosine t. And then I would have a sine t in front of the k with a negative t sine t minus cosine t. And so what will happen is if you multiply these things off, all of this stuff should cancel. This will be t sine t cosine t minus t cosine squared t minus t sine squared t minus sine t cosine t. And so the sine t cosine t's cancel. So what you're left with is just a t. And then the other part, you'll notice there's a sine squared and a cosine squared. If you factor out the negative t in common, I'm going to try to squeeze it down here on the bottom. If you factor out the negative t in common, you're left with sine squared and cosine squared again. That sine squared plus cosine squared again will be 1, so that's just t minus t times 1, which is 0. So it should come out to be 0, and it does. And if it is, then you know it's orthogonal. And you could try the other one if you wanted to. If you did b dotted with our cross product, it would also come out to be 0. All right, let's do it with a little bit simpler ones with not sines and cosines, but maybe t's and t squareds and things. So if I did the cross product for these two vectors, I would have an I, a j, and a k. I would have a t, 1, and a 1 over t, and then I'd have a t squared, and a 1. And so on the I would get the 1 over t, the t squared, and 1. Then I'd have a minus. On the j, I'd have a t, a 1 over t, a t squared, and a 1. And on the k, I would have t, 1, t squared, and t squared. And so doing our diagonals, I would do the first diagonal, 1 times 1, which would be 1. Then I'd subtract off the other way, t squared times 1 over t. One of the t's cancel, so you just get t. The next one, the t times the 1 gives you t. The t squared times 1 over t would also just be t. So those actually cancel when you do these diagonals. And the last ones, you won't have that nice canceling going on the last one on the k, but we'll end up with a t cubed minus a t squared. So I'm just left with 1 minus t on the I, and I'm left with the t cubed minus t squared on the k, and the j term actually just disappeared. And so let's do I'll check it with the b on this one, for instance. If I did the dot product for t squared, and 1, dotted with, here our dot product would be 1 minus t. I don't really need that in parentheses, so I'll take that parentheses back off. The 1 minus t, and 0, and t cubed minus t squared. I would do the first ones, the t squared times the 1 minus t. I would do the second ones, the t squared times 0, which won't do anything. And the third one's the 1 times the t cubed minus t squared. That'll give me a t squared minus a t cubed. The part with the 0 goes away, and I'll end up with a t cubed minus t squared. That indeed comes out to be 0, and so they are orthogonal. And you could do it with the a one as well. I'll leave that up to you all if you would like to try that. Okay, some properties of your cross products. If a, b, and c are all vectors, and c, not bold, is a scalar, then if you do the cross product of a cross b, it is not the same thing as b cross a. It's actually negative b cross a. You'll pick up a negative sign along the way, basically. But that's about it. If you do a constant multiple, you can put that constant multiple anywhere in there. Your associative property, distributive properties work basically how you think they would. If you do a cross b plus c, you could distribute the a on each one and do a cross b plus a cross c. Same way going the other direction with the c's. You can cross them and then dot it with a vector, or you could cross the first two and then dot the third vector. It doesn't matter about the order. The a cross b cross c ends up being the dot product of a and c times b minus the dot product of a and b times c. That's a little bit different. And if you cross the same vector with itself, you'll get the 0 vector. And then you could do, like I said, the I, j, and k are already orthogonal to each other. So I cross j equals k, j cross k equals I, k cross I equals j, and then so on. And then if you wanted to find the angle between two vectors, you could do, instead of the dot product divided by the magnitude, you could do the cross product's magnitude divided by the magnitude of each one and set that equal to sine theta. We almost never use that one because the cross product's just harder to come up with than the dot product. So we usually just do the dot product one. But a corollary to that is that one of the definitions for two vectors to be parallel is that your cross product is 0. And so if your cross product is 0, instead of being a constant multiple is probably easier to check, but the cross product will check it as well. If you cross two vectors and they come out to be 0, you are parallel. So let's try to find the vector not by doing the determinants, but by using the properties from the previous page. So I cross j cross k. That one's a fairly easy one. One of your properties on the previous page says that I cross j is k. And if you cross any vector with itself, you get the 0 vector. And so if you did I cross j cross k, you end up with the 0 vector. That one's a fairly easy one to do. The next one, not quite as easy. Okay, so if I did j minus k and cross that with k minus I, what would that turn out to be? Well, if you're crossing two vectors that are subtracted, I can rewrite that. This j minus k cross k minus I could be rewritten as j minus k crossed with k plus j minus k crossed with negative I. So that's an x there. And so then we can kind of use that property again going the other way. I could then say this is the same thing as j cross k, kind of doing distributing, minus k cross k make sure I'm okay, yeah. And don't want to mess them up. I'm trying really hard to look at them really hard. Then we'll have a j crossed with a negative I, and then we'll have a negative k crossed with a negative I. So we're basically just distributing all that stuff out. Okay, all those negatives don't really matter because you can that's just treated as a number, so you can factor those numbers out. So this could be j cross k plus negative 1 times k cross k plus, and I could pull the negative 1 out of off the I and make this negative 1 times j cross I. And there's a negative on the k and on the I on the last one, so there's a negative 1 squared that just comes off of the k cross the I. Then according to your properties, j cross k is I. So these two turn into I. These two, like above on part A, that turns to 0, regardless of whether or not there's a negative 1 in front. The j cross the I is actually negative k, and the k cross the I is j. Negative 1 squared is just 1, j. So all of that to say we end up with an I, we end up with a J, I'm putting them in alphabetical order now, and I end up with a K. So it's just I, J, and K, all added together. Isn't that crazy? But all you're doing is a lot of distributing. You got to make sure you keep all your negatives and such straight, and then they all should turn into things that are off that chart. Okay, we did a meaningful versus useless thing before in the last section, so I thought I'd do the same sort of thing in this section. For instance, if I did A dot B cross C, that is something we could actually get something out of. The cross product is a vector, and I can dot a vector with another vector. So this one is good. This is a meaningful expression. When you get done, though, it is a scalar, because a dot product will give you a number. B, that is completely useless. B dot C is a number, and I can't cross a number with a vector. So can't do anything there. The third one, B cross C, is a vector. And I can cross A with another vector. This is good. This is meaningful. And it would actually be a vector, because you're crossing B cross C as a vector. And then I can cross A with that other vector. So yeah, that's good. D, completely useless. B dot C is a number, and I can't dot a number with a vector, so that won't work. E, A dot B is a number. C dot D is a number. I can't cross two numbers. This one is useless. But the last one, A cross B is a vector. C cross D is a vector, and I can dot two vectors together. This one's okay. This is a meaningful expression. And you'll get a scalar out of it because of the dot product. So this one says, can you find A cross B and can you find B cross A? Now, if you remember your properties, you only have to do one of them, and then the other one's pretty easy to come up with. So if I did A cross B, I would have an I, a J, and a K. It's always nicer to work with numbers. 2, -1, 3, 4, 2, 1. So I end up with the -1, 3, 2, 1 determinant on the I. For J, I'll have the 2, the 1, the 4, and the 1 on the J. And on the K, I'll have the 2, -1, 4, 2. So then I'm multiplying numbers. -1 times 1 is -1, minus 3 times 2 is 6. So remember, we're doing the diagonals this way, minus this way. On the J, 2 times 1 is 2, 4 times 1 is 4. 2 times 2 is 4, minus 4 times -1 is -4. So this is -7i. 2 minus 4 is -2, but the negative in front makes it a positive 2j. And 4 minus -4 is 8, so I get a plus an 8k. That is my cross product. Or, if you wanted to write it in the same notation, -7 to 8. Whichever way. Doesn't really matter to me. And it actually won't matter on the homework either. It'll take it either way. And so if I go, if I want to find B cross A, remember, A cross B and B cross A are not the same thing, but it's -A cross B. So it just swaps the signs all the way across. So I'd end up with a positive 7, a -2, and a -8. That would be the cross. Now you could actually plug those numbers in if you wanted to. and it would come out correctly. I think I missed something. Oh, dang it, y'all. Sorry, y'all. Way back up there at the top, I wrote the J down wrong. It's supposed to be 2, 3, 4, 1. I'm sorry about that. So this actually is 4, and 4 times 3 is 12. And so 2 minus 12 is negative 10, but the negative makes it positive 10 in front. So it's not a big boo-boo, but it will mess you up. This will be a positive 10, and then a negative 10 on the other one. So sorry about that. I just noticed that I missed that number. So yeah, there you go. That's the correct answer. Negative 7, 10, and 8 for the cross product. Okay, find 2 unit vectors that are orthogonal to both of these vectors. So what I need to do is find the orthogonal vector that is orthogonal to both of these, which is the cross product, and then I'll do the unit vector of that. So my cross product, now notice it doesn't say which one is A and which one is B. You might say, well, it will matter. I won't get the same answer if I do them backwards. And that is absolutely true. That's why it says find 2 unit vectors. So if we do them backwards, I'll find one and you'll find a different one, but we're looking for 2 anyway, so then the other one would be the other one we found. And so I would end up, make sure I write this down correctly this time, 2, 1, 1, 0 on the I, minus the J would be the outsides, the 3, the 1, the negative 1, and the 0 on the J, and then the K would be the lower left, 3, 2, negative 1, and 1. So I'll get 2 times 0 is 0, minus 1 times 1 is 1. I get 3 times 0 is 0, minus 1 times negative 1 is negative 1. And on the K, 3 times 1 is 3, minus 2 times negative 1 is negative 2 on the K. So this gives me a negative I. The negative makes it positive, but the negative on the outside makes it negative again, so I'll have a negative J. And then I'll have a 5K. Or you could write it as negative 1, 5. Whichever one you want to do. That's your orthogonal vector. I need a unit vector for that. So my unit vector, if you remember, is the vector itself divided by the magnitude of that vector. So I'll have a negative 1 squared, a negative 1 squared, and a 5 squared. So I'll have negative 1, 5. On the bottom, 5 squared is 25, and 1 and 1 makes 27. So you could either leave it like that, or if you wanted to, you could do negative 1 over root 27, negative 1 over root 27, and 5 over root 27. That is a vector, that is a unit vector that has a length of 1 that's orthogonal to those 2 vectors. 27, you can simplify it if you want to. It's 3 root 3. So if you want to do that, that's only one vector. The other vector that you could have found is if you would have reversed the cross product part and put the negative 1, 1, 0 in there first. The only thing that changes is the sign. So we could have another vector of positive 1 over root 27, positive 1 over root 27, and negative 5 over the square root of 27. That would be a different vector. Same magnitude, just the other direction. So that's how you end up with both vectors. So that would be 2 vectors. Okay, one thing about the cross product is that the length of the cross product, A cross B, like the magnitude of the cross product, that would be equal to the area of a parallelogram. And so if I just drew a generic parallelogram, not necessarily these points that are on here, if I drew, say, one going this way and one going that way, if I were to move that bottom one up, I would have something like this. If I move the left one to the right, I could connect them this way, and I could find the area inside of here, which would be the magnitude of the cross product. It basically is making a plane. This is a 2D version. The one that we're going to do here is a 3D version, so these points are not the points that I'm working with here. But we usually go around the outside, labeling them P, Q, R, and S. So I only need to find two vectors. So for instance, I could go from P to Q and P to S, find the cross product between them and take that magnitude. So that's what I'm going to do here. I need to find my P to Q vector, which in our case, I would subtract Q from P. So I'll get a 3 minus 1, a 3 minus 0, and a 3 minus 2. That would be 2, 3, 1. And I want to do a P to S vector. So I need to do S minus P. 5 minus 1, 2 minus 0, 7 minus 2. And so that would be the vector 4, 2, and 5. Then I could take the cross product of those vectors and figure out that magnitude. So I'm going to have an I, a J, and a K. And I'll do 2, 3, 1, and 4, 2, 5. Now here the order won't matter because when we do the magnitude, all those numbers will get squared and everything anyway. So if you do them the other way around, it won't really matter on this problem. But the I will be using the 3, the 5. Oops, sorry, I put the 5 in the wrong spot. The 3, the 1, the 2, and the 5. On the I. And we'll have minus the J, we'll use the 2, the 5. I keep writing that 5 up there at the top. I have no idea why. You'd think I'd learn after the first time. 2, 1, 4, 5. I'm going to know this time. And on the K, well, I don't have to use the 5 at all. I have a 2, a 3, a 4, and a 2. And so I'll have 3 times 5 is 15 minus 2 times 1 is 2 on the I. On the J, I'll have 2 times 5 is 10 minus 4 on the J. And then on the K, I'll have 4 minus 4 times 3 is 12 on the K. So this is 13I. 10 minus 4 is 6, so I'll have a negative 6J. And 4 minus 12 is negative 8, so I have a negative 8K. Or you could write it as 13, negative 6, negative 8, if you would like to write it that way. Then all I have to do is find the magnitude of that. So my area would be the square root of 13 squared plus negative 6 squared plus negative 8 squared. 13 squared is 169 plus 36 plus 81. That is the square root of, let me think, see, oh, sorry, that's not 81. Man, I'm not doing too good putting all these numbers in here, am I? 8 squared is 64. Oh, that's easier to work with then. 64 and 36 is 100, and 169 makes 269. So my area is the square root of 269 square units, whatever that is. And you can type that in the calculator if you like. This example says to find a non-zero vector that is orthogonal to the plane through the points, and it lists 3 different points, and find the area of the triangle. So these 3 points will make a triangle, and we want to figure out the area of that triangle by finding an orthogonal vector. And so I'm going to do kind of the same sort of thing with a triangle. It's a little easier with the idea of how the triangle would work. I need to go from P to Q and P to R. So I'll need a vector PQ. So I do the Q minus the P. So that's -2 minus 1, or 1 minus 0, and 3 minus 1. So that gives me -3, 1, and 2. And then I need from P to R. That'll be 4 minus 1, 2 minus 0, 5 minus 1, or 3, 2, 4. So there's 2 vectors. Now I can find the cross product of those 2 vectors, and that will tell me the area of the parallelogram. So if I cross them, I'll end up with an I, a J, and a K. I'll do -3, 1, 2, and 3, 2, 4. So I'm crossing the PQ and the PR. And so for the I, I'll have a 1, 2, 2, 4 on the I. That's supposed to be a straight line. See if I can make that a little bit straighter. Minus on the J, I'll have a -3, 2, 3, 4. And on the K, I'll end up with -3, 1, 3, 2. This will give me 1 times 4 is 4, minus 2 times 2 is 4. Well, that just went away. Then I'll have a -12 minus 6 on the J. And I'll have a -6 minus 3 on the K, multiplying the diagonals and subtracting them. This will give me, the first part goes away, that's just 0. This will give me an 18J, and 6 and 3 make 9, so I get 9K. Or you could write it as 0, 18, -9. That would be my orthogonal vector. I then would want to find the magnitude of that. So this is the area of my parallelogram. How do you spell parallelogram? Parallelogram. Parallelogram. That may or may not be right. So spell it any way you want to. So the area of the parallelogram would be the magnitude, 0 squared, 18 squared, and -9 squared. So if you add all that together, we'll end up with the square root of 405, or if you would like to simplify that, that is 9 root 5. It's not asking the area of the parallelogram, it's asking the area of a triangle. But if you take a parallelogram and you cut it down the diagonal, you'll end up with 2 triangles. And that's basically the idea that we're trying to work with here. Can I come up with the area doing 2 different triangles, and those 2 triangles together make the parallelogram? And I apologize, but my mouse has disappeared from me being able to write anything. Oh, well, it's down there. So what if I do this? The area of the triangle would just be 1/2 of the 9 root 5. And it doesn't really simplify a whole lot more than that. You can make it 9 halves root 5 if you want to. But that would be your answer. You just take half of that, and that would be it. So hopefully that makes sense. Okay, I had to do a little stopping and restarting, so we're going to pick back up with this idea. If we could do the cross product between two vectors and then we dot it with another vector and find its magnitude, that's actually the formula to find the volume of a parallelepiped. If we have three vectors, A, B, and C, then their volume would be that formula, the magnitude of A dotted with B cross C. It's actually also called the triple scalar product, which is that formula as well. So if it says to find the volume of a parallelepiped determined by A, B, and C, I first do the cross product. I want to do, not A, I actually want to do B crossed with C to begin with. So we're going to do B cross C. So that'll be an I, a J, and a K. I'll have negative 1, 1, 2, and 2, 1, 4. So my I would use the 1, 2, 1, 4. My J would use the negative 1, 2, 2, 4. And my K would use negative 1, 1, 2, 1. And so this would be 4, 1 times 4 is 4, minus 2 times 1 is 2. On the J part, I would do negative 1 times 4 is negative 4, minus 2 times 2 is 4. And on the K, negative 1 times 1 is negative 1, and 2 times 1 is 2. This gives me 2I. Negative 4 and negative 4 is negative 8, but the negative in front makes it positive 8. And a minus 3K. Or, if you would rather write it as 2, 8, negative 3, that's okay as well. That's my cross product. I then have to dot that together with A. So now I have to do A dotted, that's a dot right there by the way, dotted with B cross C. So I would do A, which is 1, times the 2 from the cross product. I would do 2 from A times the 8 from the cross product. And I would do 3 from A times the negative 3 in the cross product. And so that gives me 2. 8 times 2 is 16, and a negative 9. So I have 16 and 2 make 18. 18 minus 9 is 9. Now, the volume is positive, so I have absolute values around my formula. But the 9 is already positive, so the 9 is my volume of my parallelepiped. And so that's all you're doing is you're working through that formula to try to figure out what the volume is. Or they may ask you to do a scalar triple product, and it would be the same thing. So, kind of a more formal thing. The triple products, the A dot B cross C, is called the scalar triple product. It does not need the absolute values on there because it's not doing a volume. But if you're not doing the volume and you're just doing a 3x3 matrix of 3 different vectors, you end up with a scalar triple product. So instead of an ijk across the top, we could do all 3 vectors in there at once. And if the triple product is equal to 0, then the scalars are called coplanar. So we're going to use the scalar triple product to show that these three vectors actually are coplanar, which means if I do this correctly, it should come out to be 0 when I'm done. So I want to do U dotted with V crossed with W. And so I would put across the top 1, 5, negative 2. The next one would be 3, negative 1, 0. And the last one would be 5, 9, negative 4. And though it doesn't say I, J, and K across the top, the process is the same. I would do the lower right, the negative 1, 0, 9, negative 4. But I multiply it by 1 instead of I, because the 1 for the I would be. For J, or for the second part, I would do the 3, 0, 5, negative 4. But now I'm multiplying it by 5. And for where the K would have been, I would do 3, negative 1, 5, 9, except instead of a K, I'm multiplying by negative 2. So this would be 4, negative 1 times negative 4 would make 4. 9 times 0 would be 0. 3 times negative 4 makes negative 12. 5 times 0 is 0. And then I have a multiply by 5. And then 9 times 3 is 27 minus a negative 5. Still times negative 2. So this is just 4. The negative 12 times the negative would make a positive 12 times 5 would make positive 60. And 27 minus negative 5 is 27 plus 5, which is 32 times 2, which is 64. The fact that it's negative 2, though, makes this actually a minus sign. So the negative 2 times the 32 makes negative 64. This stuff actually does come out to be 0. And so since it does come out to be 0, these things are coplanar. Coplanar. I can't spell coplanar. Coplanar. So what you're looking for is just to make sure that it comes out to be 0. Okay, torque. Here's something you'll talk about in physics. Torque is a cross product. The cross product is often pops up in physics and engineering. If we consider a force F acting on a body at a point by a position vector lowercase r, then the torque, which is lowercase tau, the torque relative to the origin is defined by the torque being the cross product between the r and the f vectors, the force and the position. And it measures the tendency of a body to rotate about the origin. So classic picture when you do the right hand rule, for instance, is that your thumb is driving in the screw where your hand is rotating the wrench kind of idea. And so I'm going to use this lower formula to come up with the next problem. So a bicycle pedal is pushed by a foot with a force of 60 newtons. The shaft of the pedal is 18 centimeters long. They ask you to find the magnitude of the torque about the point P. And so that's not terribly hard to do. One thing, though, is newtons is measured, newtons and goes with meters and things. So you can't use 60 newtons and use 18 centimeters. You have to change that to meters. But I'm going to use the formula that the torque, the tau vector, is the magnitude of the r times the magnitude of the f times the sine of theta. And so my r, the 18 centimeters, would be 0.18 meters. The force is 60 newtons. And I have the sine of 80 degrees. The 80 degrees is adding this 70 to this 10. And then you just type that in the calculator. This is 10 0.6 Newton meters of torque on that point. So that's just one example. If you get into physics and engineering a lot, you'll do a lot of these type problems. So I'm not going to focus on doing a whole bunch of those. So hopefully that's not too bad. That's the end of cross product. So we will do lines and planes after this.